Hello and welcome back. So last time we saw how analyzing a sequential circuit can be a bit troublesome. So we not only need to take into the account of inputs, we need to also consider the previous outputs to actually predict what we're going to output. And more importantly, the output isn't going to be as stable as zeros and ones in combinational circuits. As we've seen before, there are cases where it just toggles between zeros and one and never really stabilizes. So most of the time in a sequential circuit, we need to wait sometimes for a sequential circuit to stabilize on a certain value of outputs before actually writing it down on the truth table. And this is something you might see in the future. Now, let's move on to the main topic, the SR flip-flop. So before we actually get into the circuit, let's just explain the name first. S stands for set, as we're setting a bit to either 0 and 1. Well, we're setting a bit to 1. And R is the reset, which represents resetting that bit back to 0. And it's called flip-flop for many different ways. I understand it as like it's kind of symmetric, but it's not really. And at the same time, it flips and flip-flops between different values for the Q bit right here, the output bit. There's not really a concise definition of why it's called a flip-flop, but we just call it that. Now, before we actually get into the nitty-gritties and the truth table of a SR flip-flop, I'm just going to tell you what its general behavior is. So we get two states, S and R. Note here, I'm writing only down the inputs because we're only talking about the overall behavior when these inputs change. But at the same time, you need to understand when we drop down a truth table, we still need to consider previous outputs. So when the set bit and reset bit are both 0, the states, the outputs, Q and Q prime doesn't change. When the set bit is 1, the reset bit is 0, we set the Q bit to 1. And the Q prime bit is mostly an auxiliary component that makes sure that the circuit stabilizes and not like toggle as the previous example. And in all the cases we consider as valid states, Q prime is going to be the exact opposite of Q. So in this case, it's going to be 0. And when we have the set bit to 0 and reset bit to 1, we're going to reset this bit back to 0 and set this, and in doing that, we set this bit to 1. And there's one more state when it's both 1. And this is an error state for the SR flip-flop, as it gives outputs that doesn't really work out. We'll see why that is in a minute. Now let's construct this SR flip-flop in our beloved friend logic.ly. So the first button is the reset button. And then the second button is the set button. And then we have two outputs. One of the output is Q. The other output is Q prime, which is simply the opposite of Q. And then we have two NOR gates. You'll see later that it doesn't have to be NOR states to actually accomplish the goal of setting a bit and resetting a bit. But we're just using NOR gates here for demonstrative purposes. So let's do this. And what's interesting here is the outputs goes back to the inputs of another one. So this is what makes it a sequential circuit. So when you first set it up, it doesn't really know what to do yet because it doesn't have a previous output. and therefore it can't really operate until, let's press the reset button. Now Q prime is set to 0, set to 1, and the Q is set to 0. And now we turn off the reset and we set the bit Q bit back to what it was. Now whatever I do with this button shouldn't change the state of this overall flip-flop. And only when I click this button, it should reset the bit back to 0 and its complement back to 1. And whatever I do with this, it doesn't change the circuit anymore. And now back to the error state that we talked about. We can see that both outputs are zeros. Previously, we mentioned that the Q prime is simply a complement of Q, which acts as a auxiliary components to the circuit. And this is a case that doesn't make sense because, well, the opposite of 0 isn't 0, it's 1, but it's not represented here. And most of the time, you won't be using the set and reset button at the same time. So this is a state that doesn't make sense. So the SR flip-flop takes care of this weird case and says it's an error case. Now, back to the difficult part, the truth table. The truth. Wait. The truth table. This is a simplified version of the SR flip-flop. It does the exact same thing. If you want to check it out, it should be pretty obvious. I would recommend you take some time, pause the video, and try to construct this truth table yourself before I give you the answer. Yeah, I'll see you when you get back. All right, welcome back. So I'm guessing you paused and came back. So here is our answers. So, like we said before, in cases when S and R are both 0, we maintain whatever the state was. So the initial state is the same as the final state. The initial state is the same as the final state. And whenever we have the set bit to 1, the S bit to 1, whatever the initial state is, we make Q 1 and Q prime 0. So as we can see here, whatever the initial state was, Q is 1, Q prime is 0. And when we click the reset bit, whatever the initial state was, we set Q back to 0, and we set Q prime back to 1. Note in this truth table that we don't have a slot that we should for S is 1, R is 1, and Q is 1, Q prime is 0, and stuff like that. And that's because, like we said before, when S and R are both 1, it's an error state, and it's just not a case that we need to consider in the SR flip-flop. Next time we'll see how the SR flip-flop can be constructed with not a NOR gate, but a NAND gate. And we'll see how different that will be from the SR flip-flop we have right now. See you next time.